99% of the work there. Thank you for doing that. I'm going to talk about estimating network edge probabilities, which is joint work with Yuan Zhang, who is here, a PhD student of mine and Jiju, who just graduated and starting a job at Ohio State. And G, my longtime collaborator at Michigan, who actually was supposed to be here but had to cancel. So I had a whole introductory section for this talk, which I would give to a generic statistics audience, which I deleted because I think you guys can be spared. I left just this one slide just to say that what I'm talking about is more general network stuff, mostly with examples from social networks, like many talks here. But I do have two students here who are presenting posters on brain networks, inferred from fMRI imaging, which I also work on. So if you have a chance, look at their posters this afternoon.
Oh no, Liza, you've run out of batteries.
I ran it into the ground. Is this better? Okay, great. So let me just go straight to the setting and notation. And I think, fortunately, I'm using more or less the same notation that all the previous speakers did, or most of them anyway, so it shouldn't be too confusing. So we're focusing on the simple case of undirected networks, unweighted, so all the edges are binary, 0 or 1. They're represented by the adjacency matrix. We, like most of this work on estimating probabilities, make the assumption that the edges are generated independently. But at this point, we're not yet assuming anything about the probabilities that gave rise to the edges. So we think of this as a single realization from some population probability matrix. Each edge is generated independently from its own Bernoulli distribution with probability Pij. And generally speaking, the goal is to estimate that probability matrix from the single adjacency. Sometimes the goal is more specific, like in community detection, you want to estimate a certain aspect of this matrix, which is the blocks it's divided into. Sometimes the goal is something else, but generally speaking, a lot of network analysis problems fall into this framework. And obviously, if P has no structure, then there is no way you can estimate it because there is only one observation for each distribution of the different probability. So everybody, one way or another, has to assume that P has some structure, and sometimes the structure is appropriate for a particular application. One of the most common types of structure is, of course, communities, which have come up many times already. Say the stochastic block model, that's a type of structure in P. Another type of structure that people assume sometimes is monotone node degrees. So all the degrees are different, and you can order the nodes in such a way that they're increasing. That's a strong assumption, but it makes some problems solvable. You can assume that P is smooth in some sense. I'll talk a little bit more about what that means. Or you can assume that it's a generic low-rank matrix, and that's also been done. But one way or another, there has to be some structure in P that you have to use to share information across edges. Otherwise, you can't do it. So community structure, I'm not really going to go through the definition of the block model, again, because I'm not even using it. One example of structure. And I think by now we know very well how to fit this model. There are many methods that are now quite scalable and accurate. We still have a problem when the network is sparse or K is very large, but by and large we can do this. This is a special case of the more general exchangeable model, which also has come up. I think people here mostly, many of you know much more precisely what exchangeable network model means, but just loosely I'll just say it means that the labels of the nodes don't mean anything, so you can permute them any way you want, and the distribution of the network will stay the same. And there is the standard representation due to Aldous and Hoover through the so-called graphon, where we say that every exchangeable network in this class can be represented through this function and latent node positions, so-called, which are IAD uniform random variables. We don't observe f, we don't observe size, we don't observe p either, we just observe a. And so the literature on graphon estimation, which is substantial now, has mainly focused on the question of how to estimate this function f, which you don't observe. The difficulty in that, and that's a big difficulty, is that f is not identifiable, because it's only defined up to a measure preserving transformation, and that's a very large class. It's basically all the permutations of nodes. And so it's not clear how you even really talk about estimating f. You can make assumptions to make it identifiable. So monotone degrees is one reason people make this assumption, is that it makes the graphon identifiable. But it has to be strictly monotone. So for example, it rules out the block model. It has to be, they all have to be different. Or you can make some other assumptions, but you have to make quite strong assumptions. So just briefly, a subset of papers that have worked on that question of estimating f. Sophie and Patrick have several papers which propose the method that they call a network histogram, which basically approximates it with a stochastic block model with a large number of blocks. That's very much like you would approximate a generic function with a step function. Also only determined up to a permutation. Edo Iroldi and some of his students have a series of papers that all assume monotone degrees. And in that case, it's clear what you do. You sort the nodes by degree, and then you smooth in some way. Different ways of doing it. You can do generic low-rank approximations. There are many, of course, low-rank approximations. That's one of the most cited ones, I think, now is Suraj Chatterjee's paper, Universal Singular Value Thresholding. It doesn't know anything about networks. It's just a low-rank method. And so you can do that, but of course, you're going to get rates that are not as good as would be optimal specifically for the problem of graphon estimation. And we, in fact, know now what's minimax for graphon estimation, thanks, as usual, to Harry. So they've derived this minimax rate under the stochastic block model, also for smooth graphons. But that minimax estimator has a combinatorial cost. So we don't know how to compute the actual optimal minimax estimator. So what I want to focus on today is forget about the function f. Forget about the identifiability. Because in the end, what am I going to do with this f most of the time? In the end, I actually want to know p. Because a common application is link prediction. Right? Some links may be missing, some links may be noisy. You're using this information to denoise p so you have a better idea of what's where. And so that's my goal. I just want to estimate p. I don't care about size. I don't care about the latent positions. I don't care about f. I just want it for that one single realization that gave rise to the data. So that's the goal. Other goals that we can hopefully achieve is don't make, and we'll have to make some assumptions because we know we have to, but make them relatively weak, make it computable, whatever it is, needs to be efficient, and hopefully get an error rate that's not too embarrassing. So this is what we propose to do for this problem for estimating the probability matrix P itself. Generically, we call it neighborhood smoothing. You can think of A in that form. Do I have a, okay. Use this thing. Oh, okay. This was not a good move. There we go. So you can think of each Bernoulli observation as its mean plus an error term, except it has to be a Bernoulli error. And this, by the Alder-Toller representation, looks like this. So if you just look at this problem by itself, and we're definitely not the first people to point this out, this looks like a non-parametric regression problem, right? That you're trying to estimate this function. The important difference is that the xi's themselves are not observed. In standard non-parametric regression, these would be x's that you do observe. Here, we don't have the design. But if you think about it, if it's a smooth function, as you would want it to be in non-parametric regression, we don't really need to know the x's. We just need to know neighbors for a point so that we can average, so that we can smooth, right? And knowing size, of course, is one way to find neighbors. That's a good way to find neighbors. But there are other ways to find neighbors. You can just compare what we call slices of the probability matrix, columns or rows, right? And if they're similar, then they can be averaged together. And then you don't actually need to know the latent position. So assuming we can find these neighbors, and I'll say more about how we find them, this is just a very simple way of smoothing. We define that as an estimator just to symmetrize, right? Because everything is symmetric, we do it over rows and over columns. And so we just take the neighbors for each node and average. And you normalize by the size of the neighborhood. Yeah?
What's it mean for f? So f is not the natural parameter in this setting. It's the space of graph limits, and graphons are concrete representations of these. If you quotient out by, say, weak equivalence, you get the graph limits.
Yeah, so
What is, and they're defined as functions are defined on probability spaces. What might be smooth in one probability space might have no smooth equivalence in another one. So why?
So I think there is a lot of confusion that has come from the fact that people using these models started calling these graphons, which mean probability limits in the original setting, and these two things are not quite the same. And so I think it's just very confusing to try and match them together. I mean, there's at some high level they're related, but this is not quite what you're thinking. You just take it as you can just start from this model. Just say this is the model we assume. We assume this is how the probability matrix was generated. That there is some function, and there are latent variables that are uniform on 0, 1, and then this is what happens.
I can buy this as a model, but I guess I see no reason that a smoothness assumption on an arbitrarily chosen probability space is going to be reasonable.
Yeah.
So what I would say is just we assume that let's say you can consider F to be belonging to one of the equivalent classes, right, under certain permutation. So you think that two graphons can be, if one can be permuted into the other one, they're equivalent.
Right, but then if you add a whole
So
other
we just assume that within this equivalent class, one of them is.
So this is interesting, but let's just hold the discussion and give Lisa a chance to get through the rest of her talk, if that's all right. All right, thanks.
Okay, yeah, we can talk more about this. And this exact question is partly why I really didn't want to do anything with graphons for a really long time. But then eventually I gave it. But I think it makes sense in this kind of context if you just look at it as a statistical problem. Okay, so let's talk about neighborhood selection. So what we want from neighbors in this context, we want neighbors that have similar functional slices. They could be neighbors in the latent space, but they don't necessarily have to be. If you look at the block model example, the colors are not showing. You can still see the lines. So this is, just imagine this is a standard k equals 2 block model, right? These 2 points are very close to each other in the latent space, but they're actually not similar in terms of their graphon profile. These 2 points, on the other hand, are far apart in the latent space, but you could average them together, right? So if you have a smooth graphon, it's a slightly different notion of neighborhood that you actually need. So how are we going to measure this? Well, you can take any kind of functional distance you like, say L2. But of course, we cannot compute this because we don't know f, right? That's the whole problem. So can we estimate it, or can we at least get a bound on it so we can rank? That's the next step. So, and this is where we have to make some assumptions. So what we're going to assume about f is that it's piecewise Lipschitz continuous, right? So piecewise doesn't have to be globally continuous. And under that assumption, we can prove this bound. So this is the distance that we would like to compute, the actual L2 distance, and which we cannot compute. And this is something that we can compute, defined very simply as this, just the maximum of this inner product taken over all rows, which you can also write this way. This is just algebra, plus some term that as n grows go to 0. There's concurrent work to this by Aroldi which I think is still a technical report, but he sent it to us, so which we know. He is doing something else, not the same method, and he's doing some kind of clustering, but he's using a distance that's somewhat related to it. It's the mean, not the max. And I'll show you in empirical comparisons. We included this, and we'll see how they compare. So once you compute this, you can just rank, and we just threshold at a quantile, rather than try to think about an absolute threshold, because as you can imagine, right, you do a threshold on 0.01, 0.001. So we just threshold at a quantile. We can show consistency of this procedure under the same piecewise Lipschitz assumption, plus a few more regularity conditions that I don't want to go into, but they're not particularly interesting. And basically, you get convergence of p hat to p, the estimated probability matrix to the truth, and appropriately scaled Frobenius norm, and it's even uniform over this family. And it also, the theory gives you some idea of what the bandwidth should look like, because the bandwidth, that's the quantile, that matters, and there is a constant, but at least the order is given, and we empirically checked how sensitive it is to the constant, and it's not particularly sensitive. So a brief comparison with various other methods. So this method is not minimax. It does not achieve the minimax rate, which is actually something we checked when we should did, but it doesn't. But it is computable. Well, it's actually quite easy to compute. So if you compare it to, of course, this is a better minimax rate, but it's combinatorial. If you compare it to other methods, we have a reasonable combination of generality and rate. This rate is better, but it's only under the monotone degrees assumption. This, they don't have the rate. The rate from low rank is, of course, going to be not as good because it's a generic method. It doesn't take advantage of all these assumptions in the graph one. So now I should just show you a few pictures. We just made up these graphones, but we tried to do different things so that they're low rank and not low rank, monotone degree, not monotone degree, smooth and not so smooth. You can see different cases, and just specifically what we compare it to is universal singular value thresholding, two different monotone degree methods. One is just literally sort and smooth, and that's what they call it, sort by degree then smooth. They have a version which first applies singular value thresholding, denoising, and then smoothest, so that's the two. We compare it to both. I rolled this new thing based on averages, and then two histogram approximations following Sophia and Patrick's work. You have to fit this block model to do a histogram, so you have to do it somehow. So this is how we fit it, just by spectral clustering, which is a reasonable way to fit a block model that has a lot of blocks because it's a histogram, right? And then we also compare to an oracle estimator, which of course you cannot compute in reality, but this one, we actually give it the actual latent node positions, then partition them into blocks, and then just fit the block model on that. So this is about as well as you can do with a stochastic block model approximation. So here are some pictures. This is the true P. So this is a block model, but it's more or less monotone degrees, at least across blocks. And this is what we fit. This is what universal singular value thresholding does. And of course, it does well here because the rank is low. The actual rank is low. Haroldi's method does a bit worse here, but comparable. And the other things are a bit noisier. But of course, SBM does okay because it is an SBM. Right? And this is noisier because the degrees are not monotone inside the blocks, but because the blocks are all different, it still manages to sort them into blocks. So this is a relatively easy case. Here is a weird one. We set it up this way so that it's low rank. Rank is only 3. And the degrees are, well, they would have been the same except for edge effects. So they're very similar, right? So it's very homogeneous degrees. So sorting is not going to give you anything, right? And it goes up and down, but locally it's relatively smooth. Single value thresholding, again, does very well because it's low rank. So if it's low rank, it will do well. This is noisier. sort and smooth fails entirely because there's nothing to sort on. Right? So you just get weird stuff. And so does the actual fitted stochastic block model histogram, because how do you fit stochastic block model to that, right? The oracle does okay because it's the oracle, so because there are a lot of blocks. Here is something that's just a little bit different from the identity. Not quite identity, but there's like almost like a chain graph. And here, single value thresholding cannot do anything because it's full rank. So there's nothing to threshold. It just gives you an empty thing. Sort and smooth also has nothing to do. And these are reasonable versions. Slightly blurry, but something reasonable. And this is something that is also full rank, or close to full rank, and the degrees change in this kind of pattern, and you can see different things. Basically, every method gets something bright in this corner, something blue in that corner, but if you're trying to follow this kind of structure more closely, this kind of non-parametric smoothing that we're doing actually gets closer to it than any other methods because it has this ability to adapt to local smoothness patterns because we're just looking for neighbors. Briefly show our application to link prediction, which is the reason you would do that in practice. I think if you're going to estimate the matrix of probabilities, then you actually think that you don't really have this true adjacency matrix, which is what we've been using. You have a mask. This is just a simple case where some links are missing. You can also make it so that some links are noisy. So some links are present there that shouldn't be there. This is just missing. So you multiply some of them by 0 and knock them out. And what you want to do in this case, you want to produce some kind of score. It doesn't necessarily have to be a probability. It doesn't really matter. There could be scores on a scale from 1 to 100. But you just want to know what are the most likely links in this network. And you can just do an ROC curve, remove some number of links. I'm actually not going to show simulations with this. I'll just show you one real data application. This is the political blogs network, which I think everybody knows. And so we added some more baseline methods here. These three, I haven't talked about them before. These are purely link prediction methods. They do not attempt to estimate the graph on at all. They just kind of do link prediction. And sadly, on this problem, they really don't do nearly as well as the graph on estimation methods. So this tells you gain something by actually trying to estimate the probability matrix and not just saying this is just a bunch of zeros and ones and we'll just deal with them as zeros and ones. So that's a good thing. And then, there are some differences here. There's actually less differences than in the simulations. There's still some, and we actually dominated by some amount on the ROC curve, but not such a huge one. So just to wrap up, what I think the main contributions of this work is the algorithm. It's very simple. All you have to do is really square the adjacency matrix, take the max, sort. It takes a little bit of time, but it's essentially tuning free. There is this constant sitting in front of the bandwidth, but it's a number between 0 and 1, and it's not sensitive to that, so we just fixed it to something, and it doesn't really matter. I think the structural assumptions that we're imposing, the smoothness, of course it's an assumption, but it's adaptable, right? So it finds these neighborhoods. It doesn't postulate that we have blocks or anything else. And it gets, for a computationally feasible method, it gets a competitive mean square there, right? More work. This is an open problem. I don't know if there is a computationally efficient method that attains the minimax rate. Probably, but I don't know. I'm counting on Harry to answer that within the next 6 months. So,
probably. I'm surprised you said that.
Well, I don't know. I think the assumptions may change, right?
Well,
but
probably, yeah.
so, but I think there is room between, because right now the only minimax rate that we know for a computationally feasible method is for strictly monotone degrees. So I think there is some room between that and the actual minimax rate, but I don't know if it's that exact case. That I don't know. And of course, like Sophia has just demonstrated very convincingly, this is all based on the assumption of independent edges, and I think the problem with the triangles is that's really where it's coming from, because if you assume independent edges, you're just not going to end up with as many triangles as you have in a real network because of transitivity for obvious reasons, and so that's something that remains to be done. I think not just for this method, but generally for a large class of methods here. And I'll stop there. Stop here. Thank you.
We've got a few minutes for questions for Lisa. Go ahead.
You, Ale.
Oh, okay. Just a quick technical question. You said that the edges are independent, right?
The what is independent?
You assume
Edges, yeah.
edges independent, but they're not really independent if you assume a graphon model. They're exchangeable. In
So
particular,
conditional on the
right, so they're conditional
latent, conditionally on X size, yeah.
To address the triangle issue.
Yeah, so I know your goal wasn't to recover the latent positions, but given that you have an estimator for P, can you use that estimator to then estimate the latent positions, or is that just computationally too hard to do?
Yeah, I don't know how. I mean, if your estimator was a block model, then you could, right? Then you could just sort of like do clustering on that matrix, right? If it's some generic smooth matrix, we're not doing any ordering, right? The order in which P hat comes out is still arbitrary, right? So we did the smoothing, but we don't really have any handle on the ordering of the nodes. So I mean, maybe, but it's not obvious how you would go about it.
Can you give both a prediction of the link and also an estimate of your error for each dyad?
That's a good question.
If you have a neighbor that's very highly correlated, then it's probably going to be right for that one. And
Yeah, that's a very good question. We haven't thought about it. I mean, of course, in some bootstrapping way we could, but whether you could do it without the bootstrapping, just from the distances, that's
like on a
yeah, because it's an average, right?
Yeah, on a per dyad basis.
Probably, yeah.
So I want to bring up the point again that really we shouldn't be putting smoothness assumptions on the graphons, because you can construct examples of graphons in different probability spaces such that their weak isomorphism class doesn't contain any Holder continuous version. And I mean, the real parameter here is the graph limit. And maybe here's a more intuitive way of saying this problem. We have no idea really in graph theoretic terms, say, what a smoothness assumption or the existence of a smooth version in the weak isomorphism class means. And I think we should be as statisticians searching for more interpretable conditions that we can understand in terms of the data, not in terms of some, yes.
No, I agree with you. But I could have given the exact same talk, just throwing out the graphon entirely. I could have just given it with a probability matrix P in it and nothing else, and that would still be. So I'm because people have spent so much effort on estimating the graphon.
I guess, but then you'd have these parameters which, if the set of parameters change when you add one more node, and then the meaning of the meaning of a parameter is very different now.
Can I butt in as one of the people who shoved smoothness assumptions into the discussion? As far as I'm viewing it, I'm sort of thinking of it as a partial answer to when does it make sense to use a block model. So it's not saying it's only now for these conditions that it makes sense to use a block model, but it's asking, can I come up with conditions so that using a block model with a growing number of blocks makes sense, and I can understand how my accuracy behaves. So it's just defining a set where I can answer the question. I think the complete question of mapping out the space of all functions so that they have this smooth function when you're not going to a higher dimensional latent space. I asked Svante about that, and he said he didn't know the answer. So I think the answer is probably pretty hard. If a fellow Swede can't answer it, we must be in a bad situation.
More questions?
One more question.
Yes, so again, the holder assumption. I was wondering if you made some simulation where you added a spike to your matrix or your graphon, whichever way you want to put it, and see how your estimator behaves. So I had my surface, and I would probably put 1 or 2 spikes somewhere on it, and see how the estimator behave. When it breaks down, how does it break down?
That's a good question. I'd have to ask Johan if you'd ever done that. Have you ever done that?
Probably if you have a spike, our method is just going to ignore that mostly.
If it's just one spike, I think it'll just probably,
It just smooths it out.
yeah. If you had enough, right, that's all. Yeah.
Okay, let's thank Lisa again for her talk.